Technology has evolved at a rapid rate, and now we find ourselves at a point where battery properties are insufficient for current and future devices. The main problems with batteries include long charging time, degradation reducing life cycle, and not ecologically stable. In this presentation, I will outline the importance of graphene supercapacitors as an energy storage device that will make a more viable replacement for batteries in the future. Batteries have been the primary choice of energy storage regardless of how the energy was harvested. A dry cell is a common type of battery used today. It basically converts stored chemical energy into electrical energy. In the most basic terms, a battery is made up of three components: an anode, a cathode, and the electrolyte. Due to the chemical reaction within the battery, the anode builds up an excess of electrons. This causes an electrical difference between the anode and the cathode. The electrons want to rearrange themselves and displace the extra electrons in the cathode. However, the electrolyte ensures the electrons cannot travel directly into the cathode. When the circuit is closed, the electrons are able to travel to the cathode. This, in turn, provides power to any appliance along the way. This is how the battery works. Over time, this electrochemical makeup in the anode and the cathode, and eventually they stop providing electrons, and this is how a battery dies. Batteries provide us with a mobile source of power that makes modern conveniences possible. Supercapacitors would bridge the gap between conventional capacitors and rechargeable batteries. More importantly, the electrical properties of supercapacitors may completely replace batteries. Identifying the characteristics of supercapacitors and their applications, especially as an energy storage device, will revolutionize our world. A supercapacitor differs from an ordinary capacitor in two important ways. Its plates effectively have a much bigger area and the distance between them is smaller, because the separator between them works in a different way to a conventional dielectric. Like an ordinary capacitor, a supercapacitor has two plates that are separated. The plates are made from metal coated with a porous substance such as powdery activated charcoal, which effectively gives them a bigger area for storing much more charge. Imagine electricity is water for a moment, whereas an ordinary capacitor is like a cloth that can mop up only a tiny little spill. Supercapacitor's porous plates make it more like a chunky sponge that can soak up many times more. Porous supercapacitor plates are electricity sponges. In a supercapacitor, there is no dielectric as such. Instead, both plates are soaked in an electrolyte and separated by a very, very thin insulator, which might be made of carbon, paper, or plastic. When the plates are charged up, an opposite charge forms on either side of the separator, creating what's called an electric double layer, maybe just one molecule thick. The capacitance of the capacitor increases as the area of the plates increases and as the distance between the plates decreases. In a nutshell, supercapacitors get their much bigger capacitance from a combination of plates with a bigger effective surface area and less distance between them. Supercapacitors have charge and discharge times comparable to those of ordinary capacitors. In addition, it is possible to achieve high charge and discharge currents due to the low internal resistance. Batteries, on the other hand, take significantly longer to charge. For example, a cell phone battery takes 1 to 2 hours to fully charge, whereas supercapacitors would charge in less than 2 minutes. Specific power refers to the maximum power output divided by the total mass of the device. Specific power is comparable measurement for different technologies. Supercapacitors have a specific power of 10 kilowatts per hour, which is 5 to 10 times greater than the lithium-ion batteries, which is 1 to 3 kilowatts per kilogram. This property is especially important in applications that require quick bursts of energy to be released from the storage device. While batteries only have a life cycle of 500 times and higher, supercapacitors can be charged and discharged millions of times and thus have a virtually unlimited life. This makes supercapacitors very useful in applications where frequent storage and release of energy is required. Graphene is a single crystalline allotrope of carbon. We're familiar with other carbon allotropes, including diamond, used in jewelry, and graphite, used in pencils. Then what makes graphene unique is that it is made up entirely of carbon atoms arranged in a two-dimensional hexagonal sheet. This unique atomic structure, along with carbon's inherent properties, make graphene strong, light, and nearly transparent, and an extremely good conductor of heat and electricity. Unlike batteries, carbon is abundant on Earth and ecologically sustainable. Based on these exciting properties, graphene can have varied applications for future technologies. Due to the strength of its carbon bonds, graphene is the strongest material ever discovered, with an ultimate tensile strength of 130 gigapascals. Not only is graphene extraordinarily strong, it is also very light, at 0.77 milligrams per square meter. For comparison purpose, 1 square meter of paper is roughly 1,000 times heavier. What makes this particularly special is that graphene also contains elastic properties, being able to retain its initial size after a strain. Graphene's ability to absorb a rather large amount of white light is also unique and an interesting property, especially considering that it is only 1 atom thick. This is due to its aforementioned electronic properties. The electrons acting like massless charge carriers with very high mobility. One of the most useful properties of graphene is that it is a semiconductor with both holes and electrons as charge carriers and with a very high electrical conductivity. Tests have shown that the electronic mobility of graphene is very high. It is said that graphene electrons act very much like photons in their mobility due to their lack of mass. These charge carriers are able to travel sub-micrometer distances without scattering, a phenomenon known as ballistic transport. However, the quality of the graphene and the substrate that is used will be a limiting factor. Carbon is the fourth most abundant element on Earth. As a simple form of carbon, graphene is ecologically friendly, unlike most other forms of energy storage. There are different ways in which graphene can be fabricated and used in experiments. We will look into the process of fabrication and its advantages and disadvantages of Scotch tape, exfoliation, and chemical vapor deposition. Exfoliation, otherwise known as Scotch tape method, is a cheap yet tedious way for producing small flakes of graphene. In addition, exfoliation of graphene is generally of poor quality. In exfoliation, we begin with graphite block or graphite powder on a glass slide. Then use tape to peel off a layer of graphite from its block, and then repeatedly peel off further layers from the original cleaved flake until we get down to flakes that are only a few atoms thick. By repeatedly sticking and peeling back the Scotch tape, we can get one atom thick graphene. Chemical vapor deposition is one of the more popular ways to produce high quality graphene. CVD graphene is transferable to diverse substrates, making the technique versatile for many applications. In CVD, a metal surface such as copper is put into a furnace and heated under low vacuum at around 1000 degrees Celsius. The heat anneals the copper, increasing its domain size. Methane and hydrogen gases are then flowed through the furnace. The hydrogen catalyzes a reaction between methane and the surface of the metal substrate, causing atoms from the methane to be deposited onto the surface of the metal through chemical absorption. The furnace is quickly cooled to keep the deposited carbon layer from aggregating into the bulk graphite, which crystallizes into a contiguous graphene layer on the surface of the metal. One of the most exciting materials used in supercapacitor research is graphene. Graphene is a substance consisted of pure carbon arranged on a planar sheet only 1 atom thick. It is extremely porous, acting as an ion sponge. Energy densities achievable using graphene in supercapacitors are comparable to energy densities found in batteries. However, even though prototypes of graphene supercapacitors have been made, As proof of concept, graphene is difficult and expensive to produce in industrial quantities, which postpones the use of this technology. UCLA professor Richard Kainer and his graduate student Mehar El-Kadi research into graphene supercapacitors led to some amazing discoveries. They have developed a scalable fabrication process for producing light-scribed graphene micro-supercapacitors. The following 5 images outline the process used to create the LSG. Images A through C show a schematic diagram of the fabrication process for a LSG micro-supercapacitor. Image A. A graphene oxide film supported on a PET sheet is placed on a DVD media disc. The disc is inserted into a light-scribed DVD drive and a computer-designed circuit is etched onto the film. The laser inside the drive converts the golden brown graphene oxide into black laser-scribed graphene at precise locations to produce interdigitized graphene circuits. In image B, copper tape is applied along the edges to improve the electrical contacts, and the interdigitized area is defined by polyimide, otherwise known as Kapton tape. In image C, an electrolyte overcoat is then added to create a planar micro supercapacitor. In images D and E, the final images show planar capacitors with remarkably clear and high-resolution interdigitized fingers with 150 micron resolution. More than 100 micro supercapacitors can be produced on a single disk in 30 minutes or less. The devices are built on flexible substrates for flexible electronics and on-chip uses that can be integrated with MEMS or CMOS in a single chip. Remarkably, miniaturizing the devices to the microscale results in enhancing charge storage capacity and rate capability. These micro supercapacitors demonstrate a power density of approximately 200 watts per cubic meter. 200 watts per cubic centimeter, which is among the highest values achieved for any supercapacitor. The image on the right shows 2 SEM images. In the image on the right, we can clearly see the sheets of graphene oxide as they would look pre-exposure. In the image on the left, we can see porous graphene that will make ideal material for supercapacitors. Graphene supercapacitors will bridge the gap between conventional capacitors and rechargeable batteries. Energy futurists see great potential for such cheap, easy-to-produce, energy-dense supercapacitors. In many applications, these devices could either replace or work alongside batteries to make for energy-efficient devices. Because supercapacitors charge and discharge rapidly, automobiles can be replenished quickly. The efficiency of the supercapacitor is an important factor to bear in mind. In the past, scientists have been able to create supercapacitors that are able to store 150 farads per gram. But some have suggested that the theoretical upper limit for graphene-based supercapacitor is 550 farads per gram. Due to the lightweight dimensions of graphene-based supercapacitors and the minimal cost of production, coupled with graphene's elastic properties and its inherent mechanical strength, we will most certainly see technology within the next 5 to 10 years incorporating these supercapacitors. Also, with the increased development in terms of energy storage limits for supercapacitors in general, graphene-based or hybrid supercapacitors will eventually be utilized in a number of different applications. Many companies around the world are already trailing products using this technology and creating new ways to help subsidize the use of fossil fuels and toxic chemicals in our ever-demanding strive for energy.